Induction is one of the most powerful proof techniques in mathematics, and you see it all the time in computer science. It allows us to prove that a statement is true for every natural number. Here's the intuition. Imagine a long row of dominoes. You have your first domino and then a row of dominoes here. There are two things in this scenario that if both happen, if you can show that both are true, then you will show automatically that the whole row of dominoes will eventually fall. These two things are, first one, the first domino falls. And the second one is, if every domino knocks over the one after it, so if every domino knocks over the next one, then the whole row will eventually fall. These two facts are sufficient for this to be true. And it makes sense, right? If you guarantee that the first domino will fall and that every domino falling knocks over the next one, then you automatically guarantee that the whole row of dominoes will eventually fall. Induction works the same way. We prove the first case, and we prove that if one case is true, the next one must also be true. With those two ingredients, the result holds for all cases. Now let's give a more precise description. Suppose we want to prove a statement P of n about natural numbers. So n is a natural number. You want to prove that this is true. A proof by induction has three parts. First one is the inductive hypothesis, in which you assume that P of n is true for some arbitrary natural number n. It may sound a little strange because you're assuming exactly what you're trying to prove, but I hope it will make sense in a couple of minutes. Then you have the base case, in which you show that P of 0 is true. So here you've got P of n, and here in the base case you got P of 0. This is the first domino we were talking about. And finally you have the inductive step, in which, using the inductive hypothesis, you prove that P of n plus 1 is also true. So you show that P of n implies P of n plus 1. This is like showing that one domino falling knocks over the next one. One important thing to notice here is that you don't just write down P of n and move on. You use it actively when proving P of n plus 1 in the inductive step. Without using the hypothesis, you haven't really done induction. Let's see this in action with the classical formula for the sum of the first 10 integers, which is for sure the most classical example of proof by induction. The claim is 1 plus 2 plus 3 plus n equals n times n plus 1 over 2. You will often see it written also as the sum from k equals 1 to n of k. These are two ways of writing the same thing. Cool, so this statement is our P of n. So our inductive hypothesis is assume P of n is true for some arbitrary n, which means we are allowed to use the fact that 1 plus 2 plus 3 plus n equals n times n plus 1 over 2. Now to the base case. People often forget this one, but it's absolutely crucial. We could use P of 1, for example, but let's use P of 0. So all we gotta do is replace 0 in our statement. But be really careful here, because this kind of notation with the ... can be deceiving in some occasions. For example, where do I input 0 here? It doesn't make sense, right? It looks like we're assuming there's a 1, a 2, and a 3, and in this case there is not. We are summing just 0. That's why I prefer this kind of notation, because here it gets clear that we're just summing 0 numbers, which of course is equal to 0, and then we're saying that 0 is equal to 0 times 0 plus 1 over 2. This is just the formula that's part of our statement, and of course this is true. So we have our base case, and we can move on to the inductive step, in which we want to prove P of n plus 1 using P of n? Well, P of n plus 1 is the sum of the first n plus 1 numbers. And here's the part where we need a little bit of creativity. But the thing is, we can write the sum of the first n plus 1 numbers as 1 plus 2 plus 3 plus dot 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 plus n plus n plus 1, right? This is just the sum of the first n plus 1 numbers. And given the formula of what you're trying to prove, this should be equal to n plus 1 times n plus 2 over 2. We're just using this formula, but instead of n, we're using n plus 1. So this is n plus 1, and n plus 1 plus 1 is n plus 2. So this is why we have n plus 1 times n plus 2 over 2. Okay, now how can we use what we already know, meaning our inductive hypothesis, which is that P of n is true? If you take a look at what we've just written, you will see that here we have the sum of the first n numbers plus n plus 1. So this is something we already know given our assumption, right? We can replace this part with a formula that we've already assumed to be true. So n times n plus 1 over 2, and then we have plus n plus 1. So this is our new left-hand side, which is still equal to n plus 1 times n plus 2 over 2. Now, if we simplify the left-hand side, we get n times n plus 1 plus 2 times n plus 1 over 2, and this is equal to n plus 1 times n plus 2 over 2, which is precisely what we have in the right-hand side. So we have shown that if P of n holds, then P of n plus 1 also holds. Since the base case is true, and since the inductive hypothesis leads directly to the inductive step, we conclude by induction that the formula holds for all natural numbers n. Some key things to remember. You always follow the same recipe. You have an inductive hypothesis, you have the base case, and you have the inductive step. And also, you always want to use your inductive hypothesis in the inductive step in a way that you show that P of n implies P of n plus 1.